Okay, good afternoon everyone. My name is Nobu Shirai and I'm from Mie University. Today I would like to talk about a theoretical study on gel elasticity. The content of this talk has already been published in physical level letters in this April, and please check it. And the collaborator, Professor Naoyuki Sakumichi from Tokyo University, will talk about the prior experiment of this work in the final day, so please also check it. And so I like to set the goal of this talk first. This is the main result of our paper and this talk, and the comparison between experiment and theory. The experiment has conducted on bulk gel, and they measured the temperature dependence of elastic modulus. So the data were taken from those two references, and our theory could qualitatively show the temperature dependence of it. It's quite similar, and the important point is we also could explain the entropic and energetic part of it. So yeah, it's also similar curves, and the main finding of the experiment was the negative energetic elasticity becomes negative for gels, and our theory could show that property. So let's start with the introduction. So this is a movie of a contact lens dipping with a chopstick, and you can clearly see the gel's elasticity. So our interest is basically in the gel elasticity, and question is, what is the origin of the gel elasticity? So to talk about gel elasticity, it's better to compare with rubber elasticity. Rubbers, including rubber bands, are composed of polymer chain, and they are forming a network. In the case of gel, it has polymer network with a solvent molecules, large amount of solvent, and the elasticity of those two things are quite similar, but not the same. So in the case of rubber, it basically explained by entropic elasticity. So the origin of the tension or the force is based on entropy. So this state is entropically stabler than this elongated state, so that resists the deformation. And in the case of gel, it also has entropic elasticity, but that also have energetic elasticity, non-negligible energetic elasticity. So the prior experiment showed that gels are softened by energetic elasticity. So the direction of force is opposite from this entropic one, and this helps us to deform the gel bands. So in that sense, this elasticity is negative, so we call it negative energetic elasticity. And our motivation of this work is to explain the microscopic origin of negative energetic elasticity. And we can explain the intuitive origin using this illustration. So I said entropically this state is stabler, but energetically this state is stabler when we assume the attractive interaction between polymer and solvent, because it has more surface to the solvent. So this is the intuitive explanation, but we want to explain it with theoretical model and statistical physics. And so it's better to clearly define the decomposition into entropic and energetic elasticity using a equations. So G here is the shear modulus as shown in the figure. So that can be obtained by the derivative of sigma stress with respect to gamma strain. So this is the derivative of sigma, and sigma can be written by the derivative of free energy, Helmholtz free energy A. So that can be written by this, so the second derivative of free energy. And A can be rewritten by using internal energy minus temperature times entropy. So finally we get two terms. The first one is related to energy, so we call energetic contribution or energetic elasticity, and the second one is entropic elasticity. And if we use Maxwell relation, so we can deform it to this form, so using G and T, and again entropic elasticity is also written by G and T. So once we get G, the temperature dependence of G, we can decompose it to GU and GS. And important thing was shown by the experiment. So GU over G is independent of gel's polymer networks. So they use many kinds of polymer networks, and it was shown that the polymer network doesn't affect the value of this GU over G. So in this sense, we can show the existence of negative energetic elasticity only using a subchain of this network instead of dealing with whole network. And so we define the single chain elasticity based on stiffness. So K, this has the same dimension as spring constant, is defined by the derivative of force with respect to all. So this is the end-to-end distance, so the distance between both edge of a polymer, and that can be written by a Helmholtz free energy. So this is the same logic as the bulk one, and we got Ku and Ks as energetic and entropic contribution. Here again we get those equations from the Maxwell relation. So once we get the K temperature dependence of K, we can decompose it to Ku and Ks. So from now on, I want to define the model, theoretical model, to analyze the gel elasticity. And as I said, I tried to extract a single chain from a polymer network and put it on a lattice. So this is the model we used, a lattice polymer model with solvents. So here is the lattice polymer chain, which is defined by self-avoiding walk and with solvent molecules. So those light blue circles are solvent molecules, and there are three interaction parameters. So epsilon pp, epsilon ss, and epsilon ps. It depends on the neighboring pairs of the circles, and and based on the well-known reduction technique, so that also can be found in the Professor Doy's textbook, is so we can get we can exactly show we don't have to deal with three interaction parameters, but one epsilon is enough to analyze this model, and the converted model is called interacting self-avoiding walk. So this, now we only have this epsilon, and we put that onto a three-dimensional lattice, so cubic lattice. And I want to say this thing. So so if we have attractive interaction between polymer and solvent. So I explained it in the introduction. That is correspond to the repulsive interaction between in the interacting self-avoiding case. So this epsilon is intra-chain interaction between two neighboring polymer segments, and again, yeah, if there is a polymer solvent attractive interaction in the original model, that will be the repulsive one in the converted model. So we think about this repulsive condition from now on, and we put the both ends onto a one axis and to measure a stiffness. By defining the model, we can follow the equations of statistical mechanics, and so by counting the number of the conformations of the interacting self-avoiding walk, so this W is the number of conformations, we can get partition function, and put Z here, we can get A is the free energy, and if we take the second derivative of A, so then that will be stiffness. And here I did the continuous differentiation of A, but we cannot deal with it in the lattice model, so we change it to finite difference. So this is redefined K, and so we need the first and second difference to calculate this stiffness. But basically, yeah, only thing we need is these W's, so the numbers of interacting self-avoiding walks. And as I described, so Ku and Ks can be obtained once K is defined. So I defined in the previous page, so we can calculate them. And finally, we also do non-dimensionalization. So if you find hat on a variable, that means the variable is dimensionless. So let's move on to the method. So we did exact enumeration to get W function. So this is the example for n equals 6, so 6-step self-avoiding walk case, and this is the whole conformations of the n equals 6 case, and this is a kind of image of the exact enumerations. So I used the algorithm, so simple recursion with pruning. So and up to 20 steps of self-avoiding walks. So this, from now on, I want to explain the result on the n equal 20 case, and we also did the same exact enumeration and get this table of numbers, and from these numbers we can calculate partition function and stiffness and decomposition into Ku and Ks. This as the same as the definition of them. So no, in that sense, no approximation. And this is the second slide, almost the same as the second slide. So we got this main result, and we could explain qualitatively explain the result of the experiment, so the decomposition into GS and GU using KS and KU. And actually this is non-trivial because we only used a single subchain from the polymer network, and we also didn't assume a lot about chemical details of the polymer chain. So from this model we can say the negative energetic elasticity is quite general thing for substances with a effective repulsive interaction. So gels are the one of the case, and maybe for other substances it will be found. So this is the speculation from our theoretical study. So to summarize the talk, the microscopic origin of negative energetic elasticity is solvent molecule attractive interaction, and that can be, also said that effective intrachain repulsive interaction. And so this could show the generality of negative energetic elasticity. And I didn't talk about this, but we also show the existence of negative energetic elasticity in the case of continuum limit. So if you are interested, please check the paper. Thank you very much.